Hey guys, this will be one of my videos where I go over circular motion. I'll make another one going over momentum so that you guys can do your final review before the mock exam. So I think we already got to describing and diagramming circular motion. We used terms like frequency, period, angular velocity, velocity, and we drew free body diagrams for things that were moving in a circle. Remember that period is the time it takes to make a full revolution, and the frequency is the number of revolutions that you're making in a particular time span. The cause of circular motion is a velocity vector that's perpendicular to the acceleration vector, and that acceleration vector we call a centripetal acceleration if the thing is moving in a circle. And that means that there needs to be some centripetal force. We never draw this on the free body diagram, but it's like a net force. We know we're going to expect it to arise from the other forces that are acting on the object. So we would use Newton's second law, F net equals ma, but our A is a centripetal acceleration, and centripetal acceleration is v squared over r. So our centripetal force is mv squared over r. That's how we're going to analyze things that are moving in circles. The examples given in class were orbits, driving over hills, swinging a rope, and bank turns. We're going to look at two examples from the review questions. And tying to our projectile unit, we said that satellites, anything in orbit, really is just like a projectile because the only force acting on that object is gravity. So the force of gravity then would become our net force, our centripetal force, and we would set that equal to mv squared over r like we're going to see in a minute. And we should be able to measure and predict the velocity and period of things that are in orbit. So let's look at number 14. Number 14 is of a car that's driving over hills, and the problem says, well, at the top of the hill, the car briefly loses contact with the hill, and that's what gives you the feeling of the light stomach or the butterflies, whatever you want to call it. It gives you a weightless feeling. And we want to know what's the velocity of the car if this is happening. Well, you should draw a free body diagram of the car at the very top. We only have gravity acting because there's no normal force, because for a moment the car is not touching the road. So we use Newton's second law after that, F net equals ma, where Fg is the only force acting. So we say Fg is equal to ma, but the object's moving in a circle. Even though the car isn't moving entirely in a circle, for this segment we can call it close to a circle, and so uniform circular motion can be applied there. And we say that the centripetal acceleration is v squared over r, so we substitute that into Newton's second law and we get an expression that looks like that. You should notice that the masses will cancel out, and we are left with that expression. G equals v squared over r, where we are trying to isolate v and get an expression for v. Our g, of course, is the 9.8 meters per second squared constant of being on the surface of the earth. The radius is the radius of the circle the car is driving over. So when I isolate v, I should get v is equal to the square root of g r. And this is the velocity that you would need to drive at in order to, just for a moment, briefly lose contact with the road and feel no normal force. So that's the velocity for 14. For 15, we have a planet and two satellites in orbit about that planet. And I asked, what's the relationship between the velocity and the orbital distance? Meaning, if this satellite here is traveling with a velocity v, what is this velocity, or what's this satellite's velocity when it's 2r away from the planet? So we should draw some free body diagrams. Notice that the force of gravity on S2 is 1/4 the size of that of S1. And I'm going to try and make a relationship between this force of gravity and the velocity that the satellites are traveling at. And remember, we can't say that this Fg is equal to m times 9.8 because we're not on the surface of the Earth, so we need to use Newton's universal law of gravity. his expression was this big G, m1, m2 over r squared. Now using Newton's second law, we can write that, well, the only force is equal to